Okay, I'd like to talk about partial fraction decomposition. This is a way of getting integrals of rational functions um, to become a little easier to handle. But before we get into how partial fraction decomposition works, let me give you an example of what we're trying to do. So let's add these rational expressions together. 2 over x minus 1 plus 5 over x plus 3. Okay, so the common denominator is x minus 1 times x plus 3. So on the first fraction, we multiply the top and bottom by x plus 3. And on the second fraction, we multiply top and bottom by x minus 1. And then we can add them together and put them over the same denominator. And I'm just going to distribute the 2 and distribute the 5 and put everything together, and I get 7x plus 1. Okay, so you guys learned how to do this back in algebra. Now what we're going to do is go backwards. We're going to take that 7x plus 1 over x minus 1 times x plus 3, and we're going to pull that apart and make it into the sum of two rational functions. And hopefully we'll come back to where we started. And this is what partial fraction decomposition is all about. To take a rational expression like this and simplify it. Okay, so the theory of partial fractions says that when you have two distinct factors, linear factors in the denominator, like this, x minus 1 times x plus 3, this thing is going to split apart as some number a over x minus 1 plus a second number b over x plus 3. And your job is to figure out what those numbers a and b are. And to do that, we're going to get common denominators, just like we did above. And we're going to multiply the top and bottom of the first fraction by x plus 3. And multiply the top and bottom of the second fraction by x minus 1. And we're going to get, now we can combine them and put them over the same denominator. And in the numerator I get a times x plus 3 plus b times x minus 1. Okay, now look what we have. We have this fraction is equal to that fraction. And the denominator of each fraction are equal. That means the numerators have to be equal. So we can set the numerators equal. 7x plus 1 equals a times x plus 3 plus b times x minus 1. This equation tells us that this polynomial is equal to that polynomial. And when two polynomials are equal, they're going to be equal no matter what number you plug in for x. So let's plug some numbers in for x. And I'm going to pick these numbers carefully so that I make things disappear. Let's plug a 1 in. And why am I doing that? Because if I plug a 1 in, this term is going to go to 0, right? That 1 minus 1 is going to become 0. So let's do this. 7 times 1 plus 1, that's going to be 8, equals a times 1 plus 3 is 4, plus b times 1 minus 1 is 0. So I get 4a equals 8, divide by 4, and a is 2. Next, we're going to cause this term, this x plus 3, to go to 0. So I'm going to plug in an x equal to a negative 3. Okay, on the left-hand side, 7 times negative 3 is a negative 21, plus 1 is going to be a negative 20. And then a times a negative 3 plus 3 is 0, plus b times a negative 3 minus 1 is a negative 4. So we get negative 4b equals a negative 20. We divide by negative 4 and we get b equals 5. So this thing, the way we split apart that rational expression, we found a and b, and that's going to become, let's see, a was a 2 over x minus 1, and b was a 5 over x plus 3. And look what we got. That's our final expression, and that turns out to be identical to what we started with. And that's just a first look at partial fraction decomposition. There's one thing I didn't mention about partial fraction decomposition, and that is this only works if the degree of the numerator is less than the degree of the denominator. If the degree of the numerator is equal to or greater than the degree of the denominator, then before you use partial fractions, you've got to use long division. Let's take a look at an example. X cubed plus 3x squared minus 6x minus 15 over x squared plus 5x plus 6. Now the degree of the numerator is 3 and the degree of the denominator is 2. So in this problem we've got to use long division. Let's go down here and do that. Okay, so just a refresher on how long division works. What do I have to multiply x squared by to get x cubed? Well, it's x. So let's put an x here right above that 6x. And then I multiply x times each of these three terms in the divisor. And let's see, I get x cubed plus 5x squared plus 6x. And then we subtract. The x cubed minus x cubed is 0. 3x squared minus 5x squared is a negative 2x squared. Negative 6x minus 6x is minus 12x. And we bring down the minus 15. Then we repeat the process. What do I have to multiply x squared by to get negative 2x squared? Well, that's a negative 2. Then I multiply negative 2 times, again, each of these three terms. And I get negative 2x squared minus 10x minus 12. And I subtract. The negative 2x squareds cancel. Negative 12x minus a negative 10x is a negative 2x. A negative 15 minus a negative 12 is a negative 3. This is the remainder. So the result of our long division gives us x minus 2 plus the remainder minus 2x minus 3 over x squared plus 5x plus 6. Now, on this thing, we can use partial fraction decomposition. And when you write out your answer, you're going to have to make sure to put that x minus 2 in your answer. Okay, so let's go ahead and do the partial fractions on this minus 2x minus 3. And let's see, I'm going to have to erase this long division problem. Running out of room here. Okay, so let's do this. Negative 2x minus 3 over, and this thing is going to factor as x plus 2 times x plus 3. The key in these partial fraction decomposition problems is you have to be able to factor that denominator, because that tells you how this thing is going to split apart. So just like in the first example, this is going to split apart as a over x plus 2 plus b over x plus 3. And when we get common denominators and add those things together, we're going to get a times x plus 3 plus b times x plus 2 over the common denominator, which is x plus 2 times x plus 3. Then we set the numerators equal. Negative 2x minus 3 equals a times x plus 3 plus b times x plus 2. Now we're going to pick values for x and plug them in. And we want to pick numbers that are going to get something to cancel. Let's start by plugging in negative 2. Okay, on the left side, we get a 1. And a negative 2 on the right side gives us a times 1 plus b times 0. So that means a is 1. Okay, let's plug in a -3 next. And when we plug the -3 into the -2x minus 3, I'm going to get +3. And when I plug -3 into the right-hand side, I'm going to get a times 0 plus b times, let's see, -3 plus 2 is a -1. And when you solve this for b, b is going to become a -3. So a is 1 and b is a -3. So now we can go back up here and write our final answer down. Plugging that a and b into this thing. And of course, don't forget the x minus 2 that we got from long division. So here's our final answer. X minus 2, and then a is a 1, so it's plus 1 over x plus 2, and b is a -3, so it's -3 over x plus 3. Now you could have written it this way: x minus 2 plus 1 over x plus 2, and move this minus out in front. So make it minus 3 over x plus 3. Either way, that's your final answer. Please open your partial fraction decomposition guidelines. Now pause this video while you read over the guidelines. Okay, as I said before, the purpose of partial fraction decomposition is to take a rational expression and split it up into a sum of simpler rational expressions. And the way these things are going to break apart, it depends entirely upon how the denominator factors. And it turns out that every polynomial over the real numbers can be factored into linear factors and irreducible quadratic factors. Linear factors are basically degree 1 polynomials like x plus 5, 2x minus 3, things like that. Irreducible quadratic factors are things like the sum of squares, x squared plus 1. There's a bunch of other examples. And the way we break these things down is by cases. And you can see the 4 cases there on your guidelines. Case 1 consists of distinct linear factors in the denominator. Remember, this is you're only looking at the denominator and how the denominator factors. And you can see how we split that rational expression up in example 1. In case 2, we have repeated linear factors. You can see in case 2 there's an x minus 2, a 2x minus 3 squared, and an x minus 1 cubed. Those are repeated factors. That 2x minus 3 squared is 2x minus 3 times 2x minus 3. So it's repeated twice. The x minus 1 cubed is repeated 3 times. Those are called repeated linear factors. And you can see there how those split apart in case 2. In case 3, we have irreducible quadratic factors. And you can see how each of those splits apart. In the numerator of each irreducible quadratic factor, instead of having just a single number, we have a linear expression like ax plus b or cx plus d. In case 4, we have repeated irreducible quadratic factors. And again, you can see when they split those up, they split up as linear factors, ax plus b, and so on. Now, in reality, when you get to a partial fraction problem, you're not going to have something that's strictly case 1, case 2, or case 3, or case 4. You're going to have a mixture of these cases. For example, if you look at the example just below those 4 cases, we have a mixture of those cases. That x minus 1 is case 1. It's a linear factor raised only to the first power. That x plus 3 squared is case 2. That's a linear factor repeated twice, and you can see how that splits apart. It's b over x plus 3 plus c over x plus 3 squared, and we stop when that exponent of 2 matches the original exponent on the x plus 3. And that x squared plus 9 is an irreducible quadratic factor. And so that splits up as a dx plus e over x squared plus 9. Okay, we're going to do 2 or 3 examples of all this, and so you get a better idea of how this is going to work and how you can simplify those integrands that happen to be rational expressions. Let's take a look at this example. 4x squared minus 19x plus 7, and I'm going to factor the denominator. It's x plus 3 times x minus 2 squared. So, the way we're going to split this up is by looking at the denominator, the way the denominator factors. This x plus 3, that's case 1. That's a linear factor that's not repeated. So it's going to be a over x plus 3. This x minus 2 squared, that's case 2. That's a linear factor that's repeated twice. So that's going to split apart as b over x minus 2 plus c over x minus 2 squared. And why am I stopping with the square? It's because this exponent here, that 2 in the exponent, matches that original exponent of 2. Okay, so now we're going to get common denominators and combine all those into a single rational expression. And the common denominator is going to be right here. So this thing is going to turn out, after we get common denominators and combine all these, this is going to look like a times x minus 2 squared plus b times x minus 2 times x plus 3 plus c times x plus 3 over that common denominator, x plus 3 x minus 2 squared. And then, just like in the example before, we're going to set the numerators equal. So 4x squared minus 19x plus 7 equals a times x minus 2 squared plus b times x minus 2 times x plus 3 plus c times x plus 3. Now the next step is to plug numbers in for all the x's. And we're trying to get some of these terms on the right to cancel. Okay, let's plug in negative 3. And if you plug a negative 3 into this left-hand side, you're going to get 100. And if you plug a negative 3 into this right-hand side, let's see, this term and that term are going to go to 0. So what you're going to get is a times negative 3 minus 2 is a negative 5 squared is 25. So you divide by 25 and a is going to be 4. Okay, let's plug a 2 in, because if we plug in a 2, this term and this term are going to go to 0. And if we plug a 2 into the left-hand side, we're going to get a negative 15. And if we plug a 2 into the right-hand side, we're going to get c times 5. So c is going to be a negative 3. Okay, now we have a problem because there's no more numbers we can plug in that are going to make these terms on the right disappear. But that's okay, because you can plug any number you want in for x. Doesn't matter. You don't have to make things disappear. So I'm going to pick the easiest number I can think of to plug in. 0. If I plug a 0 into the left-hand side, I'm going to get 7. And if I plug a 0 into the right-hand side, I get 8 times negative 2 squared, that's 4. So I get 4a. If I plug a 0 in on that second term, b times negative 2 times positive 3, that's a negative 6b. And c times 0 plus 3 is going to be plus 3c. Okay, but we know what a is. A is a 4, right? So if I plug a 4 in for a, that 4a becomes 16. I don't know what b is. And if I plug a 0, let's see, c is going to be negative 3. So 3 times negative 3 is a negative 9. Okay, so if I combine the 16 minus 9, I get 7. So I get 7 equals 7 minus 6b. I subtract the 7's from both sides, and I get 0 equals a negative 6b. Then divide by negative 6, and b is going to be 0. Okay, so now I can plug all of that back up into my original equation. And let me scroll this down just a little bit. When I do plug those numbers in, I'm going to get 4 over x plus 3 plus negative 3 over x minus 2 squared. That b over x minus 2 is going to disappear because b was a 0. So this is how things are going to split apart. And that's my final answer. You're probably wondering, we've been here for half an hour and we haven't seen an integral. Well, let's take that last problem we did. Let's do the integral of this rational expression. 4x squared minus 19x plus 7 over x plus 3 times x minus 2 squared. And by using partial fractions, we were able to cut this up as these two integrals. I'm going to pull the 4 on the outside. And we have 1 over x plus 3 dx. And I'm going to pull the minus 3 on the outside. And it's 1 over x minus 2 squared. There. So what looked like a really ugly integral turned out to be two pretty simple integrals. So let's take this first integral down here and work on this. This is a pretty basic substitution integral. And it turns out to be 1 over w if you let w be x plus 3. And of course that's the natural log of w, which is the natural log of x plus 3. Alright, now let's take this second integral. 1 over x minus 2 squared. And again, I'm going to do a substitution. W is going to be x minus 2. Pretty simple substitution. dw is dx. So this becomes 1 over w squared. Or I'm going to bring that w up as w to the negative 2. And to get the antiderivative, I add 1 to the exponent and divide by that new exponent, negative 1. And so this becomes a negative 1 over x minus 2. And so we're finished. That first integral becomes 4 times the natural log of x plus 3 minus, oh no, this becomes plus. Here, let's put that 3 on the top. It becomes plus 3 over x minus 2. You see what happened there? This minus and that minus canceled each other out to give us that plus. And we're finished. There's our antiderivative. Let's do one more example of partial fraction decomposition. Let's take a look at this rational expression. 6x squared minus x minus 1 over x plus 2 times x squared plus 1. Okay, this x plus 2 is case 1. that's a linear factor raised to the first power. This x squared plus 1, that's case 3. That's an irreducible quadratic to the first power. So we're going to split each of those apart according to their cases. Alright, so for case 1, that x plus 2, it's just going to be a over x plus 2. And for case 3, that x squared plus 1, we're going to put a linear factor on top, bx plus c over x squared plus 1. And when we get common denominators and multiply everything together, we're going to wind up with a times x squared plus 1 plus bx plus c times x plus 2 over that common denominator. Then we're going to set the numerators equal. 6x squared minus x minus 1 equals this stuff. X plus 2. Okay. Now we're going to start plugging numbers in for x. Let's plug in, let's make this x plus 2. Let's make that disappear by plugging in a negative 2 for x. So over on the left hand side, I think if we plug in a negative 2 there, we're going to get a 25. And if we plug in a 2 here, that's going to be a times 5. And all of this is going to go to 0 because that negative 2 plus 2 is going to be 0. So a is going to be 5. Okay. Let's plug in, let's see, nothing else is going to disappear unless we plug in a 0, because 0 times that b will give us 0. Let's plug a 0 in and see what happens. If I plug a 0 into the left hand side, I get negative 1. And if I plug in a 0 on the right hand side, I get a plus c times 2. And we know what a is. A is a 5. Then we, let's see, subtract 5 from both sides and get negative 6 equals 2c. And divide by 2, and c is going to be a negative 3. Okay, what else should we plug in? And again, nothing's going to disappear no matter what number we plug in, so let's just plug something easy in. Let's plug in a 1. On the left hand side, we get a 4. On the right, we're going to get a times 2 plus b plus c times, let's see, 1 plus 2 is 3. And we know what a is. A is a 5. So 5 times 2 is going to be 10. And let's distribute this 3 over here. So we get 3 times b plus 3 times c, and c is a negative 3. Whoops, negative 3, not 9. Okay, so we get 4 equals 10 plus 3b minus 9. And the 10 minus 9 is a 1. So we get 4 equals 1 plus 3b. I subtract 1 from both sides and I get 3 equals 3b. So b is going to be 1. Okay, so we're finished. We got A, B, and C. So if you plug all that into our breakdown here, let's see, we got A is 5, so we get 5 over x plus 2 plus B is 1 times x, that's x, and C is negative 3. So we get x minus 3 over x squared plus 1. And that's our final answer. Next, we're going to do an integral with this rational expression. Let's take a look at this integral of the rational expression we were looking at previously. 6x squared minus x minus 1 over x plus 2 times x squared plus 1. And from our previous video, we saw that this is going to split apart as two integrals. 5 times 1 over x plus 2 plus x minus 3 over x squared plus 1. Okay, now this integral here, we can split that apart into two integrals. We'll copy down this first integral, and this integral is going to be x over x squared plus 1, and then that minus 3. I'll pull that minus 3 out. So we've actually split our original integral up into 3 integrals, each one of which is going to be a little easier to handle. Let's take a look at this first integral. 1 over x plus 2. This is going to turn out to be a rather simple substitution. W is going to be x plus 2, dw is dx, so this becomes 1 over w dw, which is the natural log of w, which will be the natural log of x plus 2. Okay, let's put that back in and replace this first integral. So we get 5 times the natural log of x plus 2. Now let's take a look at this second integral. X over x squared plus 1. This is also going to be a substitution. W is going to be x squared plus 1. dw is going to be 2x dx. And 1/2 dw is going to be x dx. So this, I'll pull out that 1/2. And this is going to turn out to be 1/2 times the integral of 1 over w dw, which is going to be 1/2 natural log of w, which is 1/2 times the natural log of x squared plus 1. So let's put that back in our first page. This is going to be 1/2 natural log of x squared plus 1 minus 3. Now this third integral, you can do this using trig substitution if you want, but you could also recognize that that is the arctangent of x. So we get that one for free. And we're done. There's our final answer.